Okay, in case you guys are wondering, San Marcos is about 30 miles north of San Diego. So I get that question a lot. Today, I'm going to talk a little bit about perturbation, kind of like a lot of you. Only my interest stems from looking at synchronization. So I'm interested in unintentional synchronization when people walk side by side. And I started looking at literature in neurons, and people who are much smarter than I have very good ways of looking at synchronization between two oscillators. And so from this, I've started looking at the phase resetting curve. And so just to give you a quick definition, I'm sure you're all familiar with the idea that if you perturb the swing limb during swing, if you do that early in swing, you get a flexor response, which delays or lengthens that stride, and the subsequent stride is then delayed. If you apply a perturbation later in swing, then you get an extensor response, which shortens that stride, and then the next stride arrives sort of ahead of schedule. And so I have some plots from a single subject that kind of shows the point in perturbation versus the phase shift that you get out. The transient plot is the actual stride that is perturbed, and the steady state plot here is the 10th stride after the perturbation, so whether that is shifted forward or backward in time. So in particular, I'm interested in the phase resetting curve I mentioned because it will tell me something about synchronization. But there are some interesting results that have come out of the neuron literature, one of which is that different neurons have different phase resetting curves. And so from that, I sort of wondered whether or not humans vary in their phase resetting curve. And second to that, if you vary the firing frequency of a neuron, that also has an effect on the phase resetting curve that you get out. And so sort of analogous to that, if we vary treadmill speed or walking speed, does that affect the phase resetting curve? Okay, so here's our experimental setup. We have a weight support system and a cuff that's attached to the subject's ankle. A rope pulls on the ankle at different points during swing. The rope wraps around some pulleys, so the subject is essentially moving a point along that loop back and forth. That's to try and keep that rope taut. And so there's a robotic arm that will pull quickly to induce a stumble. And so you can see it's not a very big stumble, just enough to get them to reset their gait. Okay, so some preliminary results. We're still kind of dialing in this system, but it looks like if we aggregate all of the data and just look at different walking speeds, we don't really see a difference in the curve that we get out. However, if we divide subjects into those who have a fast preferred walking speed and those who have a slow preferred walking speed, and we take the fast walkers and look at their slow treadmill speed data and compare that to slow walkers and look at their fast treadmill speed data, then we start to see a difference in the amplitude of this curve.
Can I ask a point of clarification?
Yeah.
They're phase resetting two walks. Is there a video of another walking person or a metronome, or what's the phase of their walking being compared to?
To what it was prior to the perturbation.
Imagine they have a memory of a metronome or something. And you ask them to walk to a beat or sing a song or something?
No. So we averaged the 10 strides prior to the perturbation, and then we sort of map that out 10 strides ahead where they should be.
And they do reset at all?
They reset, but it's shifted forward in time or delayed in time. And so from these data, it looks like the curve changes as someone deviates from their preferred walking speed, which would suggest that there are differences in what this curve looks like based on your preferred walking speed. So that's kind of intuitive, but a little interesting nonetheless. So I'm going to end with this slide. Our initial experiments, we had a manually operated trigger to apply this perturbation. And so we noticed that Usually, it didn't have that big of an effect, so it just caused the subject to stumble and they began walking. But there's kind of a sweet spot where every once in a while, if you got them at just the right point, it really messed them up. And so we didn't think a lot about that until we started looking at the data, and we saw this cluster of outliers that seemed to correspond to that sweet spot that really caused a significant delay in their response. And so I'm going to end there, and if you guys want to talk more about that, come and see the poster.
So this is work that was done with David Logan, who conducted the experiments, Yuri Ivanenko, Francesco Lecquiniti, and John Jaca. The question is, why do we want to perform a spectral analysis of walking? So we're interested in understanding the neural control of walking. So a key way to understand a system is to perturb it. So our approach takes the standard approach of LTI, linear time invariant systems, and extends it to perturbations of a limit cycle. So we want to characterize small perturbations of a limit cycle in the frequency domain, and then convert from the frequency domain to the time domain. So there's two issues involved. The first issue is that this phase resetting, as just mentioned in the previous talk. And the way we deal with that is we estimate phase, and we let estimated phase take the place of time. We do our analysis, and at the last step, when we convert to the time domain, we correct for our phase estimate. So we get a result that's largely independent of the exact method of estimating phase. The other issue, so once we've done that, we have a system that can be approximated as being linear time periodic. And LTP systems, if you put power in at one frequency, you get power out at multiple frequencies. So if the input is at frequency F, you get power out at F plus K times F0, where F0 is the gate frequency and K is an integer. So to do that, to analyze that situation, we use what's called harmonic transfer functions instead of the usual approach for LTI systems, which are frequency response functions. So on the right-hand side, there's a graph where we analyze the response of foot angle to a visual perturbation during walking. Every blue point means that at the normalized input frequency indicated on the horizontal axis, if you put power in at that frequency, you get a significant response at the normalized output frequency indicated on the vertical axis. So we tested all possible frequency pairs, and those are the ones we saw a significant response at. So that diagonal structure, where you have a set of diagonal lines, corresponds to a harmonic transfer function. So we can use a harmonic transfer function to characterize that response. The end result is a phase-dependent impulse response function, where that depends on two variables. The stimulus phase, which is the phase at which you applied the stimulus, on the right-hand graph, that's indicated on the horizontal axis. 0 is heel strike. And then it depends on the phase of the gait cycle at which you measure the response, which is indicated on the vertical axis. Green means no response. Red means a positive response. So in this example, a subject is walking on a treadmill with a visual scene that's moving. The perturbation signal is the velocity of that scene. It's stochastic. It has power up to 5 hertz. And the response is the anterior-posterior position of the hip, actually the average of the two hip markers in the fore-aft direction. And what you see is after some delay, so the diagonal line on the right-hand graph is a response that would occur at the time of the stimulus. So by definition, there's no response below the diagonal line. You expect the response to occur above the diagonal line with some delay, which is what you see. If you make a vertical cut through that impulse response function, that corresponds to a specific stimulus phase, in this case, 0.15, that's early stance. And it's an impulse in terms of velocity, so it's a step in terms of position. So the upper right graph shows the step response of the position of the visual scene, 1 unit in early stance. The bottom graph shows the response of the hip position And you can see there's some delay, and then when the visual scene moves forward, the subject compensates by moving forward. So we analyzed the sensitivity of this response to the stimulus phase, and there's two regimes. The first regime we call the push-off regime. So in a range of stimulus phases, an early stance, indicated by the horizontal red bar in the upper graph, you see basically the same hip response within that range of stimulus phases. But and that response occurs early swing, so right after push-off. If the range of stimulus phases occurs in late swing or very early stance, you get that the response is highly dependent on the stimulus phase. So let me just finish by saying that these two regimes also correspond to two patterns of muscle activation. The flat foot regime corresponds to a case where you see dorsiflexor activity in early stance, and the push-off regime corresponds to a case where it's too late to see that activity. Thank you very much.
Okay, thank you, Heike. So walking with a passive exoskeleton. The exoskeleton I want to talk to you about is an exoskeleton we modeled after the exotendon concept of Anthony van der Bogart, who is here in this audience. And the idea is that you have an elastic cable, a tendon, parallel to your leg, and it runs over several pulleys that are attached at the joints of the leg. So if you have a normal gait pattern, then you can imagine that the tendon changes length over one stride. So that's what you see here. And at some points, this cable will be longer than its slack length, so there will be some force in the tendon. And we have this pulley, so this results in a moment around the different joints of the legs. So if you optimize this, you can try to match these moments with the moments you normally observe in a gait pattern. So that's what you see here. So you see that if you have this exotendon, you have a lower torque at the joints for the human, and we can interpret that as a more efficient gait. And we made two important assumptions here. One is if this moment is lower, that we also have a lower metabolic cost of walking. And the second assumption we made is that the joint angles and the joint torques are invariant to the support we give. So to test this, we built the device that implements this concept. We made a few adaptations. We added an interface at the hip, the shank, and foot. We replaced the pulleys with lever arms. That's a little bit lighter. And we have a leaf spring that captures the energy storage. So here you can see me walking in the prototype. We did a small pilot study with two subjects where we recorded optical markers to track kinematics, both of the exoskeleton and on the human. And we recorded ground reaction forces and the forces in the tendons. As well, we recorded energy expenditure. We worked with three different conditions. One is walking without the exoskeleton. One is walking with the exoskeleton, but not with the springs attached. And one is walking with the springs attached, what would be the most efficient way of walking. Well, what we see here is that we have normalized normal walking as 100, and what we see, the cost function is here, the average torque at the joints. So at walking with the exoskeleton without the springs, this is more or less the same as to normal walking without the device. But with the springs, we see a reduction in the joint torques. So that's good, that's what we expected. But what we see on the other hand that if we look at metabolic cost, this does increase by quite a bit. Some is due to the mass of wearing the exoskeleton itself, but we also see that metabolic cost increases if we add the springs to the device. Well, one thing we saw is that the kinematics and the kinetics change substantially. For example, at the ankle, where we see that people walk more on their toes. So we see some adaptation to the walking. So in conclusion, we see that the mean joint torque decreases which is what we expected, but the metabolic cost increases, and we see some adaptation to device. I have some more results on my poster, and if you'd like to discuss the results or if you have some comments or suggestions, please feel free to give them, and I also have some movies at my poster, so thank you.
Individuals with below-knee amputation experience higher risk of falling and fear of falling. This might be caused by reduced balance ability. To enhance stability, as you have heard lots of talks, foot placement has got lots of attention. But for us, the ankle is only accessible resource to help to them. Hence, we got a question, can you help them using robotic ankle to improve stability? And actually, can ankle actuation, especially push-up work control, improve disturbance rejection ability or not? To answer those questions, we investigated ankle push-up control effect on stability and compared to the other actuation methods. For that purpose, we developed 3D limit cycle working model with hip and ankle actuation. Hip is actuated to gain desired step width and desired stem length by controlling hip adduction joint and hip flexion joint. Ankle joint was actuated to gain desired ankle roll resistance and ankle push-up work by controlling ankle inversion joint and ankle plantar flexion joint. These step width, stem length, ankle roll resistance, and push-up work were actuation parameters. And we developed another layer of controller which modulate these actuation parameters once a step based on state difference between nominal states and current states to enhance stability. Then we compared each step-to-step parameter control effect on stability by measuring maximum tolerable ground height disturbance, while the model worked 100 steps without falling. We characterized stability as a maximum ground height disturbance magnitude divided by leg length to normalize. Surprisingly, the ankle push-up work control allowed the largest disturbance among the individual control method. This x-axis shows each step-to-step controller, and y-axis shows the maximum tolerable random follow height disturbance. The blue bar shows step width control result, and green bar shows the foot placement control result, which is the combination of step width and stem length control. The purple bar shows the ankle roll resistance control result, and the red bar shows the push-up work control result. We also controlled all parameters once a step, which is shown as an orange bar. As you can see here, compared to the foot placement, the ankle push-up work control can accommodate 5 times larger disturbance. And we even tried 1,000 steps for the push-up work controller. And the model can handle more than 6% leg length disturbance. This suggests that the modulation of work in the prosthetic ankle can be a very effective way to stabilize amputee's gait. But of course, this is just a result of a specific controller type and particular disturbance types. If we use different controller and different disturbance, we might get different results. And we have seen many results that using foot placement, a model can recover from very large disturbance. Hence, we implemented this type of controller, and we found that using foot placement, we can get much larger disturbance recovery. But the push-up work control also showed a similar tendency. In fact, both of them can recover from the maximum disturbance before the model broke down. After the larger step-down disturbance, the model does not have a double support phase anymore. The model has a flat phase, and we think that if the disturbance is larger than this, we can inspect it, we can sense it, hence we might need a different controller strategy. Hence, again, we think that to recover from small, unexpected disturbance, ankle push-up control and foot placement are equally important. And we hope that we apply this type of controller to our robotic ankle. Thank you.
So by now, I think we can all appreciate that ankle joint push-off power and work are important for locomotion, and we've seen plenty of examples of that throughout this conference. But today, my goal is to offer a slightly different perspective. And specifically, I'm going to focus your attention to the more distal structures. For example, there are heel pad and soft tissues that can deform and dissipate energy. And there are also toe flexors that act primarily under eccentric load. And so these distal foot structures collectively perform negative work. And throughout this talk, I'll keep referring to these structures as the distal foot structures. And our main research question is, how do these structures interact? So as a first attempt to address this question, we took a known experimental condition in which the ankle joint power are known to systematically increase. So we took data from 11 healthy subjects walking barefoot. They walked at 4 walking velocities scaled by statures per second. And you can see that our data is consistent with many previous studies done. You can see that with the arrow, with increased walking velocity, the ankle joint power increases. But what's notable is what happens distally. So we use this method called the distal foot power using a deformable foot segment model. It's a slightly non-traditional technique of quantifying power, but anybody's interested in learning more about this technique, please ask me afterwards. But in terms of the negative power, we see 2 prominent phases. First, in early stance, and we can attribute this to heel pad or soft tissue deformation. And again, during late stance. And if we just highlight terminal stance, the power profiles are going in complete opposite directions. And from a purely mechanical standpoint, we can attribute this to the two most mobile joints in our body, the ankle joint and the metatarsophalangeal joint, or the MTP, or the toe joint, more commonly called. So at the ankle, the angular velocity and the moment are going in the same direction, therefore we get positive power. But at the MTP joint, the moment and the angular velocity are going in opposite directions, and therefore we get negative power. Now, from many previous studies, modeling and experimental studies, we have a great understanding to suggest that the ankle joint power are important for supplying kinetic energy to the body to supply forward momentum. But if all of that is true, what's really the meaning behind this negative work done by the distal foot? It simply could be that it's bad design by nature, but we currently don't really have a good understanding of why this happens. And perhaps there's a good biological reason for this, and others have proposed some hypotheses. One is for traction and postural stability. And another one is the idea of energy transfer through biarticular muscles. So some muscles like flexor hallucis longus and flexor digitorum longus, they both cross the MTP and the ankle joint. So some of that apparent energy loss could be going into the shank. And we agree with both of these hypotheses, but we also have our own hypothesis and our own interpretation, and that's that the distal foot structures may modulate the operating lengths, operating conditions of the ankle plantar flexors, namely the force length, force velocity, and this in turn will help regulate the magnitude and economy of plantar flexor force production. And if you're interested in what exactly our hypothesis is, please come see my poster. But this is how we're going to approach our hypothesis. So you'll use a combined modeling and experimental approach. For the modeling approach, we'll start with something very simple, something that has a single muscle tendon unit, something that acts like a soleus in an Achilles tendon. And this solely will have a variable stiffness, K, and for every stance phase simulation, we could systematically adjust the stiffness value, K, and then we can map out the effects on the force length and force velocity operating conditions. And then experimentally, we can do parallel studies. We can modify the stiffness by foot orthoses. And then we can use ultrasound imaging to track the the length and the velocity trajectories of the muscle fascicles. And then if our hypothesis is true, then there has to be some optimal foot stiffness that will minimize the metabolic cost. Thank you.
Cool.
Hi, my name is Christian Hubicki, as she said. I'm working with Jonathan Hurst and Monica Daly as part of our ongoing collaboration between Oregon State and the Royal Veterinary College. So the question I'm sure some of you are asking is, why would you even care about a unified model between birds across species? Well, the answer we give is that we think it's really critical for understanding the priorities of legged locomotion in animals. So for instance, let's say you got this cartoon ostrich. He's got to run over rough terrain, meanwhile having to balance things like energy cost and speed and injuries all at the same time. So the question is, how does he juggle all these objectives, especially when they conflict with each other, and which is bound to happen in rough terrain. So what takes precedence? Is there some kind of trade-off? Do they switch strategy? That's what we want to find out, because more important than just for birds, we think it's also important for robots too, because that's critical for optimal control to know what you have to optimize. So why ground birds? Because they're cool, for one. Many of you have seen this video by Monica Daly and Andy Bewinter. This bird is about to run over something it doesn't see coming. It thinks it's solid ground, but it is in fact not, and it keeps going. This is, I can't do that. That's pretty good. So in addition to that, birds come in all sorts of sizes. This is actually our sample set. These are our 5 species that we look at. So from quail to ostrich, it's a 500-fold mass range. That's pretty big. Not as big as Max's shrew. Did he leave? Okay, yeah, it hit a 1,000,000-fold, but this is pretty good. So the broad sample across bipedal locomotion. In addition, there's a lot of diverse mechanical features across this range, kind of like what Max showed in his stuff, except we're particularly looking at leg postures. So small animals like quail have this crouched leg posture, and we think that that has to do with intrinsic stability. And ostriches, big animals, have to support their body weight. And this helps them reduce their muscle loads by supporting their massive body weight. And this is really important because these interact with our control policies, or at least we think they may. So what are our methods for finding these objectives? Our first one is in order to actually take experiments and then sort of challenge these priorities. So here is our runway. And this is the turkey that's running across here. He's running across, but his priorities aren't being challenged heavily between injury avoidance. Yeah, it's funny. So what we want to do is introduce a plannable obstacle as opposed to this surprise obstacle that Monica showed before. So for instance, you put a little planned obstacle in there, and you want it to challenge postural demands. Now, what do I mean by that? So we have this hypothetical bird running over this. And the question is, what's he going to do on this obstacle? What's he going to plan to do? He can crouch over that obstacle and be maximally steady, or he can do something else. He can start to vault over the obstacle, onto the obstacle, and prioritize injury avoidance by not crouching so much. So we kind of force this dilemma in the bird. And we do this across all 5 species, and we can also increase the obstacle height. And this is up to 50% of its leg length. So when you have a turkey run over that, don't worry, it can actually do that. It's very impressive. Please come see my poster for those findings. I can't go into them here because I have the second method to show, which is matching things with optimal control. I want to match experimental features by taking a hypothesized objective and doing trajectory optimization. So back to our little cartoon ostrich, this is our great opportunity to look at energy cost. So that's good, but we still need a feature to explain and a dynamical model. Now this is my long-winded explanation by why you want a unified model across species. So moving on to this model, many of you have seen the spring mass model, various incarnations. It explains the energy cycling of running. It also has this very characteristic force profile that's symmetric. Problem is, our birds run with a force profile which is highly not symmetric across all cases, across all birds. So that's interesting. So we want to explain this feature using some kind of energy optimization. And we can't explain it with a passive model, so we need an active model. So we're going to take this standard old passive model, and with the same point mass and spring, and add an actuator and add a damper. And as a result, we'll do work optimal control to see what happens to the ground reaction forces. And this is what happens. It becomes asymmetric. Basically what it does, the actuator as a work optimal strategy pushes off in the second half of stance in order to recover all the energy lost in the first. So that's pretty cool. It kind of looks like the bird, but let's do something more quantitative. So let's take actual bird data. This is level running for all these 5 species. And let's take bird parameters and fit them to basically bootstrap the trajectory optimization to have the same boundary condition and masses. So then basically try to fit the spring and damping coefficients to see how close we get. And we think that is pretty good for a 2-parameter fit across all of these species. They also have very similar damping ratios as well. Thank you. So in conclusion, there's my model, this little cartoon hopping around. Don't worry, with 2 legs, it's not so extreme and it's kicking. But the GRF asymmetry can be explained by a work optimal dissipation response. At least that's how we try to explain it. And trajectory optimization is for everyone. It's pretty cool. I really think that this is how you investigate control in animals with trajectory optimization and do science with simple models. I know that's probably been said a lot today, so it's not that new, but I really believe it. But please come talk to me at my poster, and you can see more of the obstacle results. So thank you very much.
Okay, so basically I'm talking about a hexapedal running model for the sagittal plane, and I just want to motivate briefly why we work on hexapods. So we think they are very useful, or could be a very useful platform for search and rescue and planetary exploration. I emphasize could, because there are a lot of problems to perception, locomotion capabilities, autonomy, and so far I haven't seen a platform that solves all these problems, but there's progress in all the directions. So what have we done so far? We have worked on basically on gait generation for torque-controlled, actively compliant hexapod, and we were dealing with enabling the robot to handle obstacles within its walking height autonomously, and also to handle leg loss and adapt its gait. And further, we had a strong focus on vision-based terrain perception and navigation, which you see in those two videos. So currently, we're working on a new design, and we are interested in including passive compliance. First of all, to get the mechanics more robust to operate in these harsh environments. Further, we want to exploit self-stabilization, and we want to be able to jump and run. So just give the robot the capabilities for dynamic locomotion. So we hope we have a little more happy robots. And for this purpose, we have to return to basic models and just have to do our homework to understand what is necessary in the structure of the robot to achieve these behaviors. So the model we have set up is a simple sagittal plane model. We have a body with a distributed mass. We have 6 massless legs, a sprawled posture. Each leg has 2 serial elastic actuators, one in a telescoping actuator, which extends and shortens the leg, and one rotating actuator at the hip. We control all these actuators with a feed-forward pattern. It's sinusoidal for the telescoping actuators and cosine for the hip, all at the same frequency, and we group the legs in 2 tripods, left and right tripod, and they are actuated 180 degrees out of phase. So what do we see for this model? If we pick the right set of parameters, we get some very nice periodic gaits that are stable and robust and can handle step disturbances up to maybe 30% of the hip height, and also force disturbances, short force impulses, which are 10 times the weight, and no matter which direction. So what we also see is the model shows some very nice proportional behavior in between the forward velocity and the actuation frequency. This gives us some nice mean to accelerate and decelerate it. And we also see if we increase the frequency, all the oscillation amplitudes decay. Another thing is we observe leg specialization that has been shown for insects too. So this means each leg does a different thing. So they all support the body weight, but the front legs mainly brake in the horizontal direction. The hind legs mainly accelerate the model in the horizontal direction, while the middle legs do both. Now we have something interesting. The plots you have seen before, the legs which belong to one tripod have been actuated perfectly in phase. So and if we actuate them perfectly in phase, we get the left total ground reaction pattern, so we don't see a flight phase, but we see a short double support phase in between the tripods. We have very small fore-after forces, and thus very small variations in the horizontal velocity. And we have a footfall sequence which begins with the hind leg, is followed by the middle, and then by the front leg. If we now introduce a phase shift within a tripod between middle and hind leg and middle and front leg, we can see that the model behavior changes, and we can achieve at a certain amount of phase shift a simultaneous leg touchdown. And in the total ground reaction forces in the middle, you see it looks pretty much like the well-known slip behavior, the spring-loaded inverted pendulum. So you have very smooth force curves. And another interesting fact is that the pitch oscillations of the body almost decay to 0 in this case. If we further increase the phase shift, we go back to double support phase, no more flight phase, and we see again a pronounced fore-after force. Well, this has some implications, and I'm happy to talk to you about these at the poster.
Hello, my name is Hae-Won Park, and I'm working with Professor Sang-Bae Kim at MIT. My today's topic is about gait control design using impulse modulation and its application to design of variable speed robust galloping on MI cheetah robot. So here are my research objectives. I want to have a galloping and variable speed galloping and robust galloping. So it's simple. So here are our three control design hypotheses to design our controller. The first one is sagittal plane controller can be decoupled from roll and yaw control. So we can design sagittal plane controller nicely, and then we can add decoupled roll and yaw controller later. And second one is we can prescribe impulse, which means the area of this vertical force. So it means that let's say you have you run a cheetah run at some slow speed, but if you increase the speed, the period should be it's getting short. So you have to increase the vertical ground reaction force. So how much we have to increase? So we can prescribe that using this kind of simple momentum balance equation on the vertical direction. And then the last one is we want to have a state plus event-based feedback controller instead of just time-based control. So here are results of the controller. So it starts with trotting and one-step transition to gallop, and it increases speed until 5 meters per second. And look at if you look at the ground, it's not flat ground. And then it can easily handle 25 centimeter step down easily. And then I don't give any information on the ground to the robot. So here are control design process. So first we start with the modeling of the robot, and we can get 11 degree of freedom cheetah model. And second, using that model, we did gait design by using optimization. And the important thing is ground reaction force profile is one of the design parameters for optimization instead of controller torque. And then gait pattern is another parameter for optimization. And we could get open up limit cycle with a speed of 3 meters per second. And we don't do any optimization, any extra optimization for the variable speed. And then we convert the open limit cycle to state and event-based feedback control. And then ground direction force profile become a function of a leg angle. And we add a virtual spring damper around the limit cycle in the direction of pitch and height. And we added gait pattern stabilizer to stabilize the gait pattern. And aerial phase control is just simple PD control. And then we can change the speed by scaling vertical ground reaction force by impulse modulation. So this is the result of the controller. So it starts with 3 meters per second, and it accelerates all the way up to the 14.8 meters per second. And if you look at the height and pitch angle with respect to speed, actually you can see in slow speed it gallop like horse, but in opposite direction. And in higher speed, it gallop like cheetah. And the results show that it can run 33 miles per hour with 2 kilowatt energy consumption. So we did some robustness tests to model uncertainty as well. So here are AD step trial test on the rough ground. And the blue dot means cheetah could finish this AD step trial. And red dot means it cannot finish that AD step trial. And you can see that the ground is very rough. And we perturb the pitch stiffness and vertical stiffness on the pitch and height gain on the virtual spring. And over wide range of the vertical spring stiffness, it can run, we can finish the AD step trial. And then we can perturb mass, and then it still give a pretty good result. And this is 70 step down, and 120 centimeter step down with 25 Newton meter actuated saturation. And you can easily extend this controller to 3D learning. And you can see it can be recovered from very big sideways pushes. And by just changing gait pattern, we can go back and forth between trotting and galloping easily. And this is a 3D trotting controller. And this controller will be implemented on MIT cheetah robot. Thank you.
Okay, ready? My name is Shishir from Texas A&M, and I work for Aaron Ames. We have 2 robots in our lab. Amber 1, it has 5 links. It is under actuated, no feet. And Amber 2, 7 links, has feet, so it is fully actuated. Both are planar robots. So here we are trying to achieve 2D walking. And the way we achieve 2D walking with these 2 robots, which we call human-inspired control, we basically take inspiration from humans to achieve walking. Let's say I want to learn how to pick a cup of coffee. Assume that I didn't know that before. I look at a person picking a cup of coffee. I watch his hand movements, and I try to copy that. Maybe this is what babies do when they first try to learn to walk. I say maybe because I need to be careful because I'm talking to this audience. Right? So following a similar procedure, we get the human walking data. We get the joint angle trajectories, or even linear combinations of joint angle trajectories. Could be anything. Fit functions to these trajectories, and track these functions in the robots. Now, it doesn't make sense to directly, blindly track these functions which are fit to the data perfectly, so, because the dimensions of the robot are very different from that of humans. So we will have to pick those trajectories which fit the functions, which fit the data, the human data, as close as possible, and at the same time satisfy a bunch of constraints which give us realizable walking in the robots. Now, if you have noticed, I have not fit any function to this data, which is the hip position, because for Amber 1, it's under actuated. So I don't have a motor to control one of the outputs. So this is floating around. So I need to make sure that this output is within a certain region, is stable. So from a control systems perspective, we say the zero dynamics should be within a certain region. Similarly, for Amber 2, it is fully actuated, which means I can track this particular output, but I will relax this output. I say the tracking error need not be 0. It's OK to have a non-zero tracking error for this particular output. And then I say, OK, as long as this is stable, we are good. Because of which we will have a partial zero dynamics, which I need to stabilize. So we will have an optimization problem with a bunch of constraints. Now, of course, yeah, this slide is very hard to understand. It's nothing but math, but I'll explain more in detail at the poster session. And we get a bunch of functions, tracking functions, which can be used in the robot. So we apply a simple linear controller, P controller, proportional controller. It's very simple for Amber 1, and PD controller for Amber 2. And we have walking. Is there volume here? Okay, just. Is it okay? Can you hear it? Yes. Okay. Oh, I can just. No. It's okay. Okay. Now, if you have noticed, how much time do I have? Can I replay? Okay. So I'll just replay this. Okay. If you have noticed, the walking is really robust. This is just tracking. We don't have any extra algorithm to take care of the obstacles or even the disturbances. It's all happening naturally. Let me just fast forward a bit. Is it there? Yeah, the walking is human-like because of the functions that we are using, because it closely fits the humans. So you can relate to that.
Is there a hinge at the hip or a lock at the hip?
It's not a lock. It can move up and down, forward and backwards, but not sideways.
No, but can they, do the legs react against each other, or do they react against the arm?
There is no arm here.
So there was an arm in that video you just showed.
Which one? Over here? Yes, there's a torso.
It's constrained to be vertical.
Yes. No. It's not. So it can rotate around the boom. So, and the boom is constrained there. Oh yeah, that's what you meant. Okay. Yeah, the torso can turn. And this is Amber 2, which has PD control. It's fully actuated. Yeah. I guess you may ask, okay, why do humans walk the way they walk? I mean, are they robust? Are they efficient? Do they have a good mass distribution? If you personally ask me, I don't know. I don't know why humans walk the way they walk. I should be honest with you. But after doing these experiments, I feel it's good to copy. Thank you.
So today I'll be presenting work that I did together with Michiel in Martijn Wies's lab. And my work has a title that might confuse some of you. Open loop and stable are obviously terms we've heard over the last couple of days, but manipulators much less so, and specifically the kind of manipulator you see on top here for an industrial application, doing a very basic pick and place task in an unstructured environment, but without any humans around. So over the course of the next few minutes, I'm going to try to show you the overlap between our research and the research that's been presented before. And to do that, I'll just give a brief overview of the approach and leave all the details for when you come talk to us at the poster. So basically, our concept is as follows. We are trying to develop an arm for industrial applications, which means we want them to be cheap. So our plan to make them cheaper is to just strip them of all sensors they have and all the electronics needed to use those sensors. Now, that seems like a plan, but it has a problem. Mainly, these sensors had a function, partially, obviously, to stabilize the motion of our robot. So we need to somehow find open-loop stable motions. Now, to analyze this stability, we use the fact that we're doing pick-and-place motions. So they're very repetitive, so we can use the cyclic or repetitive motions types analysis. So with a little stretch of terminology, we're doing limit cycle manipulation. Now, that concept might be clear, but it's still a little bit abstract. So this is the concrete example. You see here a 2 degree of freedom robot arm from a top view, so it's moving in a plane without any gravity. What is not shown on this picture is that both joints have a motor, and in both joints there's damping. What is shown, and it's very important, is that the bottom link does have a spring, which obviously helps to stabilize this bottom link. There's no such spring on the second link, so we have to really find a motion that makes this robot stable, because if we just hold it in place, it would not be stable by itself. And to find such motions, we use an optimal control approach, where we constrain it to make a pick-and-place task, and we constrain it to be cyclic. And then we use a linearized Poincare map to analyze the stability, and we optimize for the convergence rate. Now, if we do that, we can show the results as follows. So you see the robot here, and the 3 graphs from top to bottom are position over time, velocity over time, and torque over time. So let's play it. So you see these little balls, they show the motion it makes in the graphs, and obviously you see it waving about. And after a couple of seconds, I will come in and give it a little push, and you will see that the balls of the position and velocity plots, they start to move around, where obviously we're doing open loop control, so the current stays exactly the same in the bottom graph. So I will repeat the same thing, give it an even more violent shock, and it waves around really heavily and really diverges, but it comes back after just 1 or 2 cycles, which I think is pretty neat. And yeah, so we have achieved with this something that we could call open loop stable waving. Now, the title of the talk is Open Loop Stable Manipulation, and there's a couple of challenges we still need to do for that. The first one, as you can see in the 2 plots on the side, these are the results from simulation and on the actual robot. And the thing you need to see from them is that they're different. And obviously that's very important if you try to pick something up, is that they become more similar. So this robustness against modeling errors is something we're working on. We have a video that we can show later that does a sort of direct optimization of this robustness. And we've also implemented a learning approach, which come talk to us in this poster. The second thing is it's just waving about, and we wanted to do actual manipulation. So we need to link some more motions, we need to start grabbing stuff. And for this we also need faster planning, so we're working on that. In short, what we do is in some ways different, like we're arms instead of legs, and we're fixed to the ground instead of loose ground connections, many more superficial differences. But what we're really trying to do is understand the dynamics of our system to enhance performance, and we use a very similar set of tools to allow us to do this. So I hope you will discuss these two things with us at a poster later.
My name is Daniel Raniewski. I'm a postdoc at Jonathan Hurst's Dynamic Robotics Laboratory at Oregon State. And I want to talk today about the progress we made with our robot Atreus. At last Dynamic Walking, we were showing the monopod. And over the last year, we built this biped. We built 3 versions of it, as somebody already have noticed. One is here at Carnegie Mellon. I hope everybody saw it. One is at Michigan, and Jesse gave that great talk about 3D locomotion. And one is at our lab. Just some numbers about the robot. So it weighs 60 kilograms, is about human size, 1.70 m high. There are 2 500-watt motors in each leg and 2 140-watt motors at the hips. And we control it from an internal computer with a frequency of about 1000 hertz. The most interesting feature that we are using are springs that are coupled to the motors and build series elastic actuators. What you see here is the force length relationship for different leg lengths, so the passive compliance of the robot, and they form a softening stiffness in the leg. And when we control the robot at our lab, we try to allow the robot to play out this passive dynamics to the largest extent possible. And what we'll see now is, after the robot danced into his gait, a quite compliant gait that we achieved. And this gait is really trying to get as much energy stored in the springs as possible. And so, second, that was too fast. Okay, so just some numbers on that gait. We stored about 260 joules in each spring. We walked at 0.7 meters per second, and what we have currently is cost of transports electrically about 1, and mechanically between 0.15 and 0.4. I have to mention that the torso is still locked to the boom, so that is our next step. What we see here is some grounded running steps. You see the single hump force profiles, and this slide that fortunately didn't show up showed typically walking force profiles that with their single humps. At one point, we were also able to make the robot hop. I don't know, something is just not right here. I hope that video will show up. Here we are. So this is work of Michael Jones, one of our graduate students, and he could make the robot hop on one leg, what is pretty impressive given the weight of the robot. So I hope to see you at my poster to talk about our next steps and to answer your questions. And just as an acknowledgement, that work
would not be possible without all the undergraduate students that work in our lab and who are really doing a great job. Thank you.
They helped us to support some of you getting travel grants. Disney Research is actually very close to where you are. You are in this building. Is there a pointer? Yep. Thank you. This way. Oh, you are right here now, and Disney Research is right across in the CIC building, directed by Jessica. One announcement that they ask us to make is that please do not post pictures of the Disney robot exhibit that you will see in the robot demonstration session later today. The second announcement is a big thank you to all the people that helped us. You know, wait. A little story. By definition, we are all scientists, like your host, your four hosts are scientists. And by definition, that means we are incapable of any management. So without these 30 additional people that helped us running this conference, it wouldn't have turned out the way it did. So please help me thanking all the volunteers and administrators.
So Mark and I, we did our PhD together at ETH Zurich at the Autonomous Systems Lab. So even though I left ETH and I'm now in Michigan, we decided to do this together at ETH. And the plan is to have it right downtown in the heart of Zurich at ETH in the main building. Here we go. Here in the main building. Everything in one place, very similar to all the other meetings, create a very intimate, collaborative environment where everything is in the same place. We're trying to sort of work with the fact that Zurich or Switzerland is not the cheapest place on the planet, so we're trying to get at least basic accommodation for free for everybody so that you can afford coming there. I think it will be a great venue. ETH has a lot of research in robotics. There are 4 or 5 groups doing robotics, 3 of them working on leg robotics. We have work in rehabilitation robotics. We have biomechanics people. And then nearby, we have the University of Zurich. We have the Balgrist Hospital, where the locomotive is coming from. We have a veterinary clinic doing sports medicine for horses. We have the Disney Research Center in Zurich doing also working in simulation and robotics. With legged systems. And to give you a sort of a small impression how we think the whole thing will look like, here are a couple of pictures of a summer school that the 2 of us hosted 2 years ago at ETH. Maybe some of you have been there. I know, recognize some faces. And we're trying to sort of take that spirit, create something that, that's very intimate, a lot of interaction, very, very informal setting to get you there. We try to revive some of the things we've done. So, for example, we try to show you a horse running on the treadmill, do something with the veterinary clinic, take advantage of the other things that are around there. So, and then, of course, you're going to see a lot of robots. You're going to play around with a lot of robots. And sort of to get you an impression, I don't know, up on the left corner, that's the accommodation that we have in mind for free. It's an old air shelter. So these are, in fact, triple bunks, 10 in a row, 20 people in one room. It sounds horrible, but the feedback from the summer school was this is the best bonding experience ever. So if you want to get to know people, you have to share 2 showers with them and your friends for life. Okay, I don't know, Marco, you want to add something to this? Okay, so then we hope to see you all there. Have a productive year until then. Thank you.